Hello, now we are going to look at when we would use multiplication as part of solving probability problems. And to do that, we're going to have a look at a three-sided spinner and a normal coin. So our spinner is a piece of card that has been cut into a triangle, and we have our letters drawn on its sides. We punch a hole through the middle of it, and we put a pen through that, and we spin it around like a top, like a spinning top, and whichever side lands down on the table, say this side lands on the table, then B would have been the outcome of spinning our spinner. So that's how that works. And flipping a coin is just a normal coin. We have a 50-50 chance of getting heads or tails. So if we look at this situation here, what is the probability of getting a B on the spinner and a tail on the coin? Well, I have used this diagram to map out the different things that can happen, to try and keep track of them. I could get an A on the spinner, a B on the spinner, or a C on the spinner, and they're all equally likely. Or I could get, and on my coin, I could get a head or tail in each case. So if I got an A on the spinner, I could get a head or tail on the coin. Well, if all of these things are equally likely, if we then look at the situation we're asked about, I would be interested in if I got a B on my spinner and then I got a tail on my coin. Well, if I have three equally likely outcomes for my spinner, then a third of the time I would expect to get the B on the spinner. And then half of that time I would expect to get a tail on my coin. So half of the time that I flip a coin, I would expect to get a tail. And a third of the time that I play my game with my spinner, I would expect to get a B. So if I combine those two things, so I'd say I do the spinner first, but it would work out the same way, numbers-wise, either way. If I, a third of the time, get B, then half of that third of a time, I'm going to get a tail on the coin. So a third of the time, I'm getting my first desired outcome. I'm getting the B. And then half of that third of the time, I'm getting the second thing I want. I'm getting a tail. So a sixth of the time, I would expect to get the B on the spinner and the tail on the coin. And does that make sense in terms of my other way of doing probability, which is just to work out the sample space, all of the things that could happen, and then see how many of those outcomes I want? Well, this diagram that branches out, my tree type diagram, shows me that there's 1, 2, 3, 4, 5, 6 different ways that this could play out. I could get an A and then a head, an A and then a tail, and so on. So there's 6 different ways that this could play out, and there's only one of them that I'd be happy with. So I would have one thing out of 6 that I would want, so I get a probability of a sixth that way as well. So I can see how this argument of a third of the time I get my B, and then half of that third of a time I'd get a tail on my coin. Now if I think about what these fractions mean, a third of the time, well, that's the probability of getting a B, and a half of the time is the probability of getting a tail. So what I can see is the probability of getting B and a tail ends up being the probability of getting B multiplied by the probability of getting a tail. That turns out to be the meaning of my argument that I used to get my sixth. So I can multiply my independent outcomes, my outcomes from each one of my events, and use that to get the probability of one thing and another thing happening. So let's put this into practice here. We're going to keep using the same spinner. So the spinner being referred to in this question, these questions, is the same as the one we have over here. So what's the probability of getting C for the first time on the fourth spin? Well, if we're looking for getting a C, all that matters to us is we either get a C or we don't get a C. So we either get C or not C. So the probabilities I'm interested in are the probability of getting a C, which I know is a third. A third of the time I'm going to get C. And then the probability of not getting a C, the other outcome I would be interested in contrast to my C. Well, 2/3 of the time, because A or B would be not getting C, so 2/3 of the time I would not get C. So what's the probability then if I spin the spinner 4 times that I get a first C on the 4th spin? Well, how could that happen? Well, to get the first C on the 4th spin, I have to have not gotten a C up until then. So I'd have to not get a C, and not get a C, and not get a C, and then finally on the 4th go, I would get C. And I know from my work down here that that's going to be the same as multiplying all those things together. So the probability of not getting a C multiplied by the probability of not getting a C times the probability of not getting a C times the probability of getting a C. That all gets a little bit cramped. But we know that this argument should work. So 2/3 of the time I'm going to not get a C, and then 2/3 of that time I'm going to not get a C, and 2/3 of that time I'm not going to get a C, and then I want to get a C. So that's my situation written out with my fractions, and I just multiply everything together. So I end up with 8 all over 81. And that's my probability of getting a C for the first time on the 4th spin. What's the probability of getting a second B on the 3rd spin? So we're interested in the probability of getting a B, which we know is a third, and then the other thing that could happen is we could not get a B, which would be 2/3, because we could get either an A or a C. So that's all of our possible situations dealt with. And now we can tell ourselves this story, the probability of getting a second B on the 3rd spin. Well, how could that happen? We have to be able to tell ourselves this kind of story. Probability of getting a second B on the 3rd spin. So a second B on the 3rd spin. Well, we could have started out by getting a B, and then we could get not a B, and then we could get a B again. Well, that would be getting the second B on the 3rd spin. But we could also, or we could have gotten not a B on the 1st spin, and then we could have gotten a B and then a B again. And that meets our description as well. That's still getting the second B on the 3rd spin. So we have 2 different things that would meet this criteria, that we'd be happy with based on this description. So what we have to be able to do then is just deal with these. We're going to multiply this out and multiply this out, and we know if we're happy with one thing or another, we can add those 2 probabilities together, because we'd be happy with either of them. If we were counting up all the things we'd be happy with, we'd be adding them up. So when we have 2 things we'd be happy with, we can just add them together. So if we calculate this, we'd have the probability of getting a B is a third, times the probability of not getting a B is 2/3, times the probability of getting a B is 1/3. Or we'd be happy with not getting a third is 2/3 of the time, and then a third of the time we get a B, and a third of the time we get a B. So if we multiply all of that out, I should have my equal sign in here, I end up with 2 all over 27 plus 2 all over 27, and I put that into my calculator, and I get 4 out of 27 is my probability of getting my second B on my 3rd spin. So what is the probability of getting all C's for 4 spins? So we just get a C, and then a C, and then a C, and then a C. Well, how would that happen? Well, we just have to get C, and then a C, and then a C, and then a C. And that's it. So we need to know our probability of getting a C, which I should have written down first. So we know the probability of getting C is going to be a third. In this case, we don't need the probability of not getting a C, though we already know it's 2/3. So all we would have to do is multiply them together. A third of the time we get a C, and then a third of that time we get another C, and a third of that time we get another C, and a third of that time we get another C. That's all that's happening. So we have a third of the time we get a C, and a third of that time, and a third of that time, and a third of that time we get all C's. So we multiply all of that together, and 1 out of 81 times we would get 4 C's in a row. Finally, the probability of getting 1A in 3 spins. So we spin the thing 3 times and we only get 1A. Well, what are the different things that can happen? Well, we can get an A a third of the time. We could not get an A 2/3 of the time. So I've laid out what I know. And how can I get 1A in 3 spins? Well, I could get an A the first time and then not get an A after that. That would be and not get an A and not get an A. That would be 1A in 3 spins, but I could also, or I could get not an A and then an A and then not an A again. That also meets my description. Or I could get not an A. I could get a B or a C, I mean. Or I could get not an A. And then finally I could get an A. And all 3 of those meet the criteria. They all meet the description that we've got. So we can write them down. The probability of getting an A, a third of the time I'd get an A, and then 2/3 of that time I'd not get an A, and 2/3 of that time I'd not get an A. And I'd be happy with the other outcomes, so I add up all these probabilities. 2/3 of the time I'm not going to get an A, then a third of that time I'm going to get an A, and 2/3 of that time I'm not going to get an A again. Or, so I add up, 2/3 of the time I'm not going to get an A, and 2/3 of that time I'm not going to get an A, and 1/3 of that time I'm not going to get an A. So I multiply all of that out together, and I get 4 all over 27. And as it happens, it's the same for each one of them, 4 out of 27 plus 4 out of 27. So I add all of those up together, and I get 12 out of 27, and I have a common factor of 3, so I divide that out, top and bottom, and I end up with 4 all over 9. And that is how we can use multiplication to help us with solving probability problems. And that is what we need for now.